All right, everybody. For our last session before lunch, our speaker is Aforza Polin, who is an assistant professor of statistics at the University of Wisconsin-Stout, and she'll be speaking about multiple testing in high-dimensional and correlated data. Thank you.
Thank you, everyone, for attending this session. So I'll talk a little bit about the multiple testing problem for high-dimensional data. So first, I will just discuss the background of this modeling and discuss some results. So we start from a linear regression. So we know that this is a mathematical model or statistical model we use to predict the response based on some predictor variables. So X you see here in this regression model are the predictor variables that we use to predict something. That something is our Y. We called it response variable. So how many, it doesn't really matter how many variables you are using, you will be close to your real the response variable, but it will not be exactly accurate. Say, for example, if you are trying to predict the student's grade and use lots of variables to predict their grade, still lots of students with same numbers for different variables may not have the same grade. So then you see that last number, the notation is called epsilon, that is the error. That means there is a gap between your prediction and the actual numbers. So this is a classical problem in statistics we usually do in I think in almost every sector, not in statistics. But high-dimensional data, these days we get lots of variables because we have lots of data. Especially if you think about the genetics, we have so many variables, so then it's important to understand which variables are important. So not all of them are important. So by the definition of high-dimensional data, we say when your number of covariates, that means number of predictor variables, will be larger than the number of sample size. So this is the thing usually we test in our classroom, like how do we predict the effect of the variables, that is called the beta. Beta measures like how the variables, say for example, attendance impact students' grade, how they are, like how early they choose their measure impact their grades or other things. So beta measure that coefficient, that means the impact of that variable on the response variable Y. So usually we do ordinary least square, that means we want to minimize the gap between our response variable and our prediction, like the actual response and the predicted response. But we cannot just minimize just the gap between Y and X beta. So X beta we called it predicted because we assume that the mean of epsilon, that means the mean of error, is 0. So however your data is, you will always come up with 0, the mean error. So that's why we do, like we called it least squared mean error. So the number of beta that minimize your error, that means the squared error, we called it least squared error. That means you estimate the beta that gives you the minimum error in terms of squared. Now, if I have a data, say for example, I created a data that has 5 sample size and our predictor variable 6. So my n is smaller than x. And if I want to calculate this one, so I need, x is a matrix, so the transform of x, like x times x. And you can calculate x times x, that's completely fine, that will give you a number. But when you want to calculate the inverse of that, then it says it's not possible because you are getting something that has 0 columns, that means singular matrix. So we need to overcome from this situation to handle that kind of data that has number of predictor variables larger than the number of sample. So there are several approaches. One is called sparse regression model. That means we believe that not all the predictor variables are important. Few of them are important. Most of them are not important. So that means you are going to use a sparse regression. That means exclude the variables that are not important. And there are lots of directions. So two other directions are called sufficient dimension reduction. That means you will reduce the dimension by keeping the structure same. Like k variables will give you the same productivity as p variables, and k will be obviously less than n. And like there could be like linear combinations or any other combinations of variables. That means actually in different format you are trying to minimize or you are trying to reduce the number of predictor variables in your data. So one of the important procedure or one of the important method of sparse regression is lasso. This is very discussed technique over this time when we have this large number of variables. And so it's a penalized least square. That means you imposed a restriction on the coefficients. And k is called the budget parameter. That means it tells you like how minimize by which amount. So if k is small, then you are actually choosing smaller number of predictor variables. If k is large, then you are choosing large number of variables. And in that case, overfitting, k is small, underfitting. So we need an optimum value for k so that it's not overfitting, not underfitting. So we actually do this lambda. These days we do it through cross-validation. So we set different values of lambda and see which values of lambda gives you the minimum error. So, and lasso estimates actually depends on the choice of lambda. So beta hat, actually the least square estimates, that is our classical estimate of beta. And so it's add lambda with the parameter estimates if beta hat is a positive number. If it is a negative number, then it subtracts lambda from the parameters. That means it push lambda to be away from 0. And what happened in last case, you see, like if it's something close to 0, then it push all those numbers to 0. That means you are getting rid of those variables. That means beta j forced to 0 if they have a smaller coefficient, means the variable that has a smaller effect on the response variable, it tells that you can remove these variables from your data. You do not need them, from your model. You do not need them in the model. Now, the bottom line is that by adding and subtracting and forcing some of this beta to 0, it's actually creating some unbiased estimate. So we will show some results like when I was presenting this to a group of like machine learning, they said, lasso is unbiased. I said, yes, lasso did some great job. It does, but it is unbiased. So we were trying to remove that bias from the lasso. So we write lasso as like the orthogonal projection on the complement of x. That means you remove the jth variable from the data and project j from the other variables. And for lasso, we cannot actually do that one. So we because it creates the zero column. So we can subtract this one from the original value minus the predicted value. And then this is the lasso estimate in terms of that orthogonal projection. Now you see we have beta j and some term here and some product of our random error. So we are not worried about that random error because by our assumption or properties of random error, the mean will be 0. So if you take the mean of beta j hat, then you will have beta j plus some terms, and this will be mean of epsilon equals 0, so this will be 0. So the middle one actually creating the problem, and that is causing the bias. So how can we get rid of this bias? So if you can get an estimate of beta k, which will be in asymptotically same as beta k, and you subtract that one, that means you can reduce the bias. So that is called debiased lasso. So we get an initial estimate for beta k and subtract that one from your lasso estimate, and that is the debiased lasso. So asymptotically, the debiased lasso is unbiased, and the variance of beta j hat, that means the debiased lasso, has some closed format like asymptotic variance. We can calculate that one. So sigma squared is the variance of the residual, which we need to estimate. We need to estimate it in linear regression too from our data. So that is the actual response and the predicted response, the difference between them, and the square sum of their squares, and divided by the, we call it degrees of freedom, n minus number of parameters you want to estimate. Usually, if we consider the classical regression problem, we need to estimate p number of parameters. But in this case, we say p number of parameters are not important, only S0, that means the number of important variables in our model. So S0 is the number of important variables in your regression model. And then we calculated the standard error. So that is the square root of this term, and estimated standard error because sigma is unknown. So we need estimated sigma. So when we do inferences, we actually do two steps. First step, we do the hypothesis testing to check, does this variable, like the predictor variable, has impact on our response? And if it has, like if we can reject our null hypothesis, that means beta j is significantly different from 0. In that case, you want to, we are curious, like say for example, if we find in our study that attendance has an impact on grade, then we want to know most of the time how much impact does it have on attendance. So we want to estimate that beta. So first, for testing hypothesis, we need to set up the null hypothesis and the alternative hypothesis. So the null hypothesis say it has no impact, alternative hypothesis say yes, it has impact, and then the test statistic is the your estimated value minus the value on the null hypothesis. Most of the cases we set equals 0. So this is mainly the ratio of your parameter estimate divided by the standard error of that parameter estimates. And it asymptotically follows t-distribution with degrees of freedom n minus number of effective variables, that is S0. And the confidence interval, we add and subtract the margin of error. That means with beta j hat, add the quantile 1 minus alpha over 2 quantile. Like if you want to be 90% confident, then t-distribution is symmetric, so 5% lower and 5% upper. So it will be the quantile, you need to add and subtract them. Now, for multiple testing simultaneously, if most of the time we want to know the impact of several variables at the same time, say, what is the risk of that if we skip this part? Like we say, in this case, like we are 95% confident that beta 1 will be a number within this limit. But in that case, so I'm 95% confident, that means I'm accepting the error that this estimate may have 5% error. Then when we test, say 10, I have 10 predictor variables, so we want to estimate or test 10 parameters at a time. And in that case, your coverage probability will be 95 to the 10. That means close to 60%. So 60%, that means you do not need to do any test. You can just say yes or no by default. So as you are increasing the number of predictor variables, you see that risk of like true coverage, like the percentage of true coverage or chance of true coverage is decreasing. So we need to consider that part. So our contribution actually in this part, that we did the multiple testing for that high dimensional data, so we use the family-wise error rate. That means you select alpha for the entire family. That means that the probability that at least one of this entire family will be rejected, like true hypothesis will be rejected, and that number should be less than alpha. So the Bonferroni adjustment, this says if you test M hypothesis, then you need to divide alpha divided by M to compare your p-values when you make that inferences. And our process works not like very well, but in a small setup, it worked well to maintain the family-wise error rate. And this is now you think about this one, if we have alpha, say M equals 10, and if you say alpha equals 0.05, then add 0.05 divided by 10 is 0.005. Sometimes it is hard to get a p-value as small as that. So the Holmes procedure, they says instead of adding like 5% to everyone, you can say order them and then compare the smallest one, say t equals 1, alpha over m, and the next highest, and t equals 2, t equals 3, and the last one actually when t equals m, then it will be, you are comparing. So set up a different cutoff for different p-values instead of just the same cutoff for everyone. And next procedure, they also say almost the similar thing, but it says if this process said start from the smallest cutoffs, that means if the smallest cutoff miss that goal, then you reject the whole process. It says instead of doing that, you can start with the large one and then gradually go backward. And then another process, they said you can start with the largest one, but check for everyone, not just stop the process for the rest of the part. Check them everyone whose variables has significant, whose variable does not. So we checked all these 4 processes in our result, in our simulation process. So I'm going to skip this longitudinal data part. It says like we have repeated measures from the same observations is repeated over the time. So the basic idea for regression is that the observations are independent, but in this case, like if you observe the same person over the time or same unit over the time, they are related because it's the same person or the same unit. So they are correlated, though the different observations are independent, but the repeated observations from the same person or same unit will be correlated. And we said like there are different methods available. So we use the process that you can decorrelate the correlation by finding the covariance, like the pattern of the correlation between them, and then do some transformation. So we generated a data in simulation with 80 our sample size, and 150 will be the number of predictor variables, and the setup for this one. And we repeated this process only 100 times because actually it takes longer time, very long time to run this one. I know that I wanted to do it 1,000 times. So currently I get access to the University of Wisconsin high dimension, like high speed data analysis part. So I think that will help to improve my like the simulation. So I said lasso is bad. It's not bad. So when you do the prediction, you see the blue dots are the actual, the red represent lasso, and green represent debiased lasso. And in most cases, you will see that the red one is close to the black one. That means when you do the prediction, lasso does a very good job, but debiased not. For prediction, lasso is good, but when we want to estimate the effect of some specific variable, in that case, it's, say I started with my process, first one is 1, second one 2, third one 4, then 3, 3. But lasso predicted my number 1 close to 0, and 1 little less than 1, 3. So 4 comes close to 3, and 3 comes below 2. But when you do debiased lasso, still these numbers, because it's just only 100 simulations. So, but these numbers are pretty close to their original numbers. And then we calculated the coverage probability for the confidence interval, 95%. So for this number, actually I said, out of this, my 150 variables, 3 variables are important. This says 5 variables are important, and this is the scenario, 15 variables are important. So you see, this process kind of works well for low number of S0, 3, and 5, but it does not work very well when we have 15, makes sense. Like you have 15 variables, still it's like kind of high dimension. And when we considered the power, we calculated power, and we see that for 3 variables, we have power 72%, 75%, sometimes like a different structure of data. And still the numbers are good. But for 15, we see that the performance of this technique is like not as good as the smaller number of S0. So family-wise error rate, like the type 1 error, so you can multiply this number with 3 and compare it with 0.05. And this is for S0 5, and this is for 15. And so we saw that this debiased lasso controlled the family-wise error rate in multiple testing, and experts regression model performs pretty well. It has some limitations, but the regression model is not, when the regression model is not enough sparse, that means we have still 15 S0 equals 15 in our regression model. So the future work for this, like I'm working on the high dimensional longitudinal data part that we said, like we do the transformation and then fit this similar model for that longitudinal data. And for non-Gaussian, that means if the response variable is not normal. In that case, we cannot just use the linear model. We need to use the GLM, means generalized linear model. And similar part, like for the binary, we use usually the logistic regression, and in this case, we need to use generalized estimating equation for the longitudinal data. And then we need to adjust the effect of the high dimensional. So I think I'm close to that. Any question?
First off, great talk. Thank you for speaking to us. Second, what's the downside of using the unbiased estimator? Like, why would we ever not use the unbiased version of lasso?
Good question. So if you do the prediction, you do not need to worry about the biased or unbiased. But when you want to do the inference, say for example, you want to say what is the impact of the attendance on grading, then you actually want to measure that will be close to, so we do not know what is like, what you get from your data. Is it the same as we say the true effect? Is it the same as the true effect? But when it is unbiased, that means you have a large sample, then you are getting closer to that true effect. So if it is biased, then it's maybe far away from your true effect.
Right, but then why would I not use the unbiased estimator?
So we prefer to use unbiased, but for prediction, lasso is working well. But yes, go ahead.
Is there any circumstance where I would not want to use the unbiased estimator?
If it is an inference question, then we will not use unbiased. Because why do we need to use unbiased like that? So we used lasso for the prediction because you cannot use the general, like the classical regression in this case, because the process fails, because you have more predictor variables as compared to the sample size. And you cannot do that part. Then you need to do the penalized least square, and the outcome of that process is actually unbiased. Sorry, the biased.
So it's just not possible in the regression setting, is what you're saying?
No, it is not possible if you have number of columns more than the number of rows. Here.
Thank you.
Yeah, thank you for the question.
Hello. I think you discussed at the end possibly looking at like a non-Gaussian case. Like, how would that potentially affect things? Or
Say, for example, if you have count data, then we need to do Poisson regression, and then your link variable, so it will not be y, will not be a linear function of beta. Then you need to adjust that link variable. And similarly for binomial, say if you have yes/no variable as the response, like is that person going to have a heart disease or not? Or is that the customer is going to buy this product or not? It may depend on lots of things. So in that case, your y is not a linear function of x.
Any last questions for Aforza?
Yeah, second. So how did, I think I at the end you sort of made a connection between the unbiased estimator and the using like the Holmes procedure, the Bonferroni, to lower the FWER. I didn't understand exactly why this was connected to it being unbiased, right? You could do it with the biased or the unbiased estimator. Like what is the distinction when you're using the unbiased estimator when you're trying to control the FWER?
Okay. Yeah, so we need a test statistic for testing, and our test statistic needs to follow a distribution. So if we look at this, like, so we have our estimator on the numerator and the standard error in the denominator. And when you calculate the mean, so we say it's like it follows t distribution. That means its t distribution is symmetric about 0. So you expect that it's the mean of this test statistic will be like it will be approaches to 0 when you have a large sample. So I think that's the idea. So when you want to estimate the parameter, so we want that this, what is the properties of that estimator? So this estimator needs to be closer to the true parameter. So I have a picture, but that's not for this one. Say, can I use that one? Okay, it's not related to one. That's the thing when I usually discuss the unbiased things. Why do we need that one? Say you want to measure the center. And I remove this blue circles. And these are the, you only see this blue dot, sorry, the black dots. So if you want to measure the center, say this is your biased estimate. So they are, and it has very low standard error. So every time you measure that one, you go close to that number. Then if I remove these blue circles, where will you measure the center? You will measure the center here. So you are doing a wrong prediction. But in this case, you get, so in these two cases, we have unbiased, but our variation is small. So you say, for example, you ask one person, where is the library? He says, go to the right, take a left turn, and then go there. Ask another person, he says the same thing. So if that direction is correct, then you are there. If both person tells you the wrong direction, then you are very confident that I'm going to the right place, but actually you did not find the library there. So this is the risk of getting low standard error. If it is unbiased, then you are good with that because you are very close to the true one. Usually we do what we do. We have only one estimate because we have one data set. We do not usually have to estimate the same thing. We have 100 data set. In simulation, we can do that, but for real life, we have only one data set. So now, if you have higher standard error, again, if you remove these blue circles, you will estimate the center here. So that is unbiased again. If you remove these blue circles, you will estimate something here. So that is important that you need to have an unbiased estimator of your parameter so that when you repeat this process and take the mean, and then we hope that you will get the true parameter estimates. Otherwise, you are going to a wrong direction because we do not know what is the true parameter is. We are just trying to estimate that one, say what is the impact of attendance on grade. We do not know. We get the a sample from University of Minnesota, another one from Wisconsin-Madison, another one from another university, another one. But if you see that these results are going in the same direction, but it needs to be unbiased. Otherwise, they all may go in the wrong direction if the technology or the methods you are using does not follow the property that it's unbiased estimate. Yes.
Thank you so much for the talk. And I understand why we're using lasso here is because like n is greater than p, so you want, n is smaller than p, so you're trying to condense the number of p's until you get to S0. But you would kind of still have to do the same thing with just a high number of parameters, even though n is greater than p, I'm wondering for even like, say we're not considering dimension reduction, we're not applying lasso or ridge or any other dimension reduction techniques. It seemed to me like it's so important to like control for multiple testing in regressions. I want to know like what is the implication? Like, is that kind of following the same procedure? And my other question is like when it comes to non-Gaussian response variables like Poisson and negative binomial, what is it that we need to adjust for there in terms of the formula? Is there anything, or is it just kind of applying the same correction on those fronts?
Please correct me if I understand your question. So first, so you said if we do not have unbiased estimator.
Oh, well, sorry, I don't really care about the bias here. I'm just wondering, like, if you're not reducing the number of parameters, if you say just irregular regression, you still care about like buffer
so
regression,
if this
correct?
is the case that our n is less than p, then you cannot do the regular
Right,
regression.
I understand that.
But if you have n greater than p, but still p is large, then you will have an overfitting model. What is the problem of overfitting model? It will do very good for your data set, but when you will predict something outside the data set, that performance will not be good. So that is we call the overfitting. That means you do not need that many variables. Yes, we do lasso for model selection to find the important variables, which variables are important for your model. Lasso, if it is not high dimensional, lasso does model fitting for low dimensional data too.
Gotcha. And my second part of that question is like with non-Gaussian response variables, do you need adjustment for the correction? Like,
Yes.
Okay.
I'm not sure if this is a workable question, but in lasso regression, is there a risk of underfitting? I mean, like I know we talked a lot about overfitting, but is there how big is the risk for underfitting the model?
Usually, if you estimate the parameter perfectly, then I will say no risk of underfitting.
All right. Thank you very much, Aforza.
Yeah, thank you much. Thank you for the questions.